In this module, we'll talk about theoretical and percent yields. By the end of this module, you should be able to calculate a percent yield based on both the theoretical and experimental yield of a reaction. So up until now, we've assumed that the amount of product we produce would be the maximum amount possible based on the amount of reactants. The reality is that we cannot produce as much product as we actually calculate. If we go back to our sandwich analogy, what we know is that sometimes we drop something on the floor, somebody steals a piece of turkey from our sandwich, and we can't make as many as we had originally planned based on our supplies. For a reaction, sometimes what happens is it simply doesn't go to completion for a variety of reasons that are beyond the scope of this course. Other times, we will lose some substance. If we're producing a gas or using a gas as a reactant, sometimes we lose some of that in the transfer process. We can also have situations of unrecovered product, either because it's spilled or because we have it, say, solid stuck to a filter paper that we can't remove from that. So lots of different things can happen to affect our percent yield. And this is a big issue when you start to look in industry, because even reducing their waste and increasing their percent yield by a small amount can make a dramatic difference in the bottom line. So the calculations we've been doing up until now have been for theoretical yield, or the maximum amount of product possible. For our example, using the snowman, we determined that our yield, our theoretical yield, or calculated amount, was 3, because that was the maximum number of snowmen that we could build from the parts that we had. We would still have some excess reagents, but we were limited by the number of snowman heads that we had. While the theoretical yield gives us the maximum amount we can possibly make, the actual yield is what we really get when we run the experiment. This is sometimes also called the experimental yield because it's what results when we actually do the reaction. What we do know is that it will always be less than, or it could be equal to, but more than likely it's going to be less than the theoretical yield. And if we go back to our sandwich analogy, if I had the supplies to make 6, and someone stole a piece of turkey off the counter, then I'm only going to be able to make 5 now. And so my actual or experimental yield is less than my theoretical yield. So when we do calculations, we're calculating the theoretical yield. The experimental or actual yield has to actually be measured after we do the real experiment. So we can actually quantify the difference in these two values by using the percent yield. And it basically shows us the efficiency of a reaction. Manufacturers are very concerned about percent yield because increasing the percent yield even by a small amount can be a large savings cost in the amount of reactants and less waste that they have to deal with after the experiment is complete. To find the percent yield, we get the actual yield, or what we actually did in our experiment. So this is the experimental yield, what we actually measured out after we did the reaction, and our theoretical yield, and this is the calculated value. And so this is either based on simply the amount of one reactant and knowing the other is in excess, or we might also combine this type of problem with the limiting and excess reagent problem, where we have to actually first identify the limiting reagent to determine the theoretical yield of a particular reaction. We do want this value to be as close to 100% as possible. That doesn't always happen, and sometimes the values are very low, even in the 20 and 30% yield. But for those particular reactions, that may be outstanding. It depends on what you're comparing it to. But we want to get as close to 100% as possible. What that's telling us is that we've produced an amount of product that is very similar to the amount we calculated we could get based on the amount of our reactants. The question we want to ask is, can this percent yield be greater than 100%? Well, the answer is no, because if it was greater than 100%, what that would mean is that the actual yield has a greater value than the theoretical yield. And we've already determined that the calculated value is the maximum amount that can be formed or produced. So if you get a value greater than 100%, there are two things you should check. 1, make sure you've done your calculations correctly. And 2, if you've done the actual experiment, to look back through and see if there's something else in that sample that you're actually weighing along with it, such as a wet sample. So you're actually weighing the mass of water and your product rather than just the product alone. So let's look at an example with the percent yield. What is the percent yield if the theoretical yield for a particular set of conditions is 0.750 grams and the actual yield is 0.606 grams of zinc sulfide? So we're given the balanced chemical equation, and we can look at the information given. We're given the actual yield, which is 0.606 grams. We're given the theoretical, which is 0.750 grams. Now I simply need to calculate the percent yield, which will be equal to 0.606 divided by 0.750 times 100. And when I do that, I end up with a percent yield of 80.8%. This tells me I got 80.8% of what I actually expected to get. Not a bad return on my reaction. Let's look at a problem that uses percent yield in a slightly different way. If we start with 42 grams of potassium chlorate, what is our theoretical yield of potassium chloride in grams? That's the first question. The next part is, if the reaction runs at an 87.3% yield, what was the actual yield of the reaction? We're given a balanced chemical equation, and what we need to do is find our theoretical yield first of the KCl. So, just like any other stoichiometry problem, we start with our 42.0 grams of KClO3. Then we use our molar mass of KClO3, which is 122.55 grams per mole of KClO3 to get 2 moles of our reactant. Then we use our mole to mole ratio, which is given in the balanced equation. We see that we have 2 moles of KClO3 to 2 moles of KCl, because that's the product that we're interested in. And then we can figure out the mass of the KCl that is produced in the reaction by converting from moles of KCl to grams of KCl. And again, we'll use the molar mass, which is 74.55 grams per mole of KCl. Now we can do the calculation to find out the actual theoretical yield. And when we do that, we find that we get 25.5 grams of KCl. Remember, this is our theoretical yield, or the maximum amount we can produce, because this is the calculated value. Now, for the second part of the equation, we're given the percent yield, we know our theoretical yield, and we're looking to find the actual yield. And so you're actually going to get an opportunity to solve the second half of this problem. So here we are. We're given the same mass of KClO3. We just calculated the theoretical yield. Now you can find the actual yield, since we're given, in this case, the percent yield. We're still going to use the same formula to solve this problem. We're just going to have some different information going into it. The equation for percent yield equals actual over theoretical times 100. In this case, we know our percent yield is 87.3%. We don't know our actual yield, that's what's being asked for in the problem, but we do know our theoretical yield, which is 25.5 grams of the KCl times 100. Now we can divide both sides by 100 and get 0.873, and then multiply both sides by 25.5 and get our actual yield in units of grams of KCl. And what we find is that we have 14.4 grams of KCl as our actual yield. This is also known as the experimental, because it's exactly how much we got when we did the real experiment. In the next module, we're going to look at solution concentration.